Hello, my name is Sébastien Kelbuch, and today I will present Hera, a framework for fault-tolerant sensor fusion with Erlang and GRISP on an Internet of Things network. Hera was created by Vincent Verpoten and myself under the supervision of Professor Peter Van Rooij at the Université Catholique de Louvain. In this presentation, I will first introduce the concepts of Internet of Things and sensor fusion. Then I will explain the issue we have with traditional IoT architecture and low-cost devices for IoT. Next, I will present the Hera framework, its purpose, its sensor fusion engine, and its software architecture. After that, I'll briefly talk about fault tolerance and give examples of sensor fusion with Hera. Finally, we'll conclude and give insights about future work. For those of you who are not familiar with the concept of Internet of Things, it is a large number of low-power devices located at the edge of the Internet and that communicates wirelessly. Now, sensor fusion is the ability to combine information coming from multiple sensors to get a single view of a situation. It is more accurate, more reliable, and more informative than if we were relying on a single sensor. Before I start explaining the problem with current IoT architecture, I want to stress that currently the IoT is growing faster than the cloud. So this graph shows the market share for microchips in different sectors and the growth. And it reveals that the demand for microchips in the cloud is much lower than in the IoT. Currently 5% versus 13%. So the traditional IoT architecture consists of cloud and fog computing. We have a pyramidal infrastructure with the edge node at the bottom, some intermediate fog nodes for data preprocessing, and the cloud at the top for the heavy computations. While this structure is very good for scalability, it has serious disadvantages. First, it's a very complex infrastructure. Not only do we have to build the actual IoT application, but we also need to develop software for the fog nodes and the cloud servers. Of course, the cloud also comes with associated costs and a latency that might be prohibitive for some latency sensitive applications. And that's not to mention that the edge to cloud connection might also be surprisingly unreliable. So to solve this issue, we want to get rid of the cloud and live at the edge. And Erlang is a very good choice for that because of its native support for concurrency, scalability, and fault tolerance. Raspberry Pi and Arduino are two examples of popular devices for IoT. On this kind of device, we usually work close to the hardware, which involve reading datasheets and even soldering. And of course, these devices are usually programmed with low-level language. C is a very popular choice. It turns out that working close to the hardware tends to increase the complexity of IoT projects, and it is error-prone. And it is even worse if we include distributed computing and fault tolerance in the picture. The GRISP platform is a much better choice. It's a low-cost embedded system that boots directly into an Erlang virtual machine. So we have all the great benefits of Erlang at our disposal. Not only that, but it also has PMOD connectors and drivers for the most popular PMOD sensors. And because GRISP takes care of the hardware, it truly is a plug-and-play system. Yet, it doesn't really address fault tolerance and doesn't provide a sensor fusion model for sensor fusion applications. And that is why we need to develop a sensor fusion framework. Hera provides an efficient and user-friendly framework to enable sensor fusion experimentation by a large public. But what does Hera do? Hera provides a sensor fusion engine, takes care of the hardware thanks to GRISP, and handle failures. So what the user needs to do? Provide the sensor fusion parameters and bootstrap the cluster of nodes. That's it. For the sensor fusion engine, we decided to use the Kalman filter. The basic idea is to start from an initial estimate of the state, and then use a physical model to predict the evolution of the state. Then we compare it with an actual measurement and combine them optimally. The key insight is to find the right balance between noisy sensors and a float prediction model. The Kalman filter has several advantages. First, it's a well-established technique in wireless sensor networks. Second, for the physical model, we just need differentiable equations. Third, there are many variations for optimization. And last but not least, it allows for asynchronous measurements. In other words, as soon as we have the information from one sensor, we can use it to update the state of the system. We don't need to wait for all of the sensors. However, defining the physical model is not trivial, but there are many examples in the literature, so the user will find a way to achieve what he wants. The software architecture is divided into three parts. On the left, there is the GRISP runtime library, which contains a full Erlang OTP and drivers for the PMod modules. On the right, there is the Hera framework, and in the center, we have the client application. This is where the user will define two kinds of callback modules. A sensor interface that simply acts as an interface between the drivers and the Hera framework, and a sensor fusion model where user defines the parameters for the sensor fusion model and also fetches the appropriate data from the local data store of Hera. He will also use the libraries to perform the actual sensor fusion computation. This approach is very modular. Now, if we take a broader view of the system, as you can see, every board is running the Hera framework, and the data flows from the sensor through the sensor interface. It is then forwarded to the framework, which shares the data via UDP multicast with all the boards. The data is stored on a local data storage, and we can use it in the sensor fusion model to perform the actual sensor fusion computation. And then again, the result is shared with all of the boards. Now, if the user wants to visualize the data, it suffices to run the Hera framework on a computer. This is an example of an application that estimates the orientation of a board. Of course, all of this is happening in real time. There are two considerations that makes fault tolerance important in IoT. First, there are multiple points of failure. It could be a hardware failure. For example, if a board is powered by a power pack, it could run out of power, or it could be a network issue. But it could also be a bug in the driver or more likely in the user code. The second consideration is that we believe sensor fusion is hard enough and the user should not do defensive programming nor error handling. So how does Hera achieve fault tolerance? Well, first, Hera has an asynchronous model. It means we're able to compute with the available data without blocking. Hera is also a dynamic system, so new nodes and processes can join or leave the system at any time without breaking anything. We're also using supervision tools of Erlang, and we encourage hardware redundancy. That is to have redundant sensors and multiple nodes that computes the same thing. And that's how Hera ensures to perform sensor fusion as long as one GRISP board is alive. In the paper, we've proved fault tolerance by performing fault injection, which consists of disabling parts of the system and observing the reaction. But I won't detail this now. An example of sensor fusion represented in the paper consists of estimating the position and velocity of a model train with 3 GRISP-Base boards. On the train, there is a GRISP board with an accelerometer, a gyroscope, and a magnetometer, and on the floor, we have 2 GRISP equipped with a sonar. And that's almost the entire code used for this sensor fusion computation. First, we fetch the data from the local data store. Then we define the sensor fusion parameter in a matrix form with Jacobians in this case. And then we use the libraries to perform the actual sensor fusion computation. That's how easy it is. It really is the bare minimum. Another example that we provide in the paper is an attitude and heading reference system, AHRS. We use a gyroscope along with an inertial navigation model to predict the orientation of a device. We also use an accelerometer and a magnetometer to find a direct cosine matrix, which we use as a measurement in a quaternion-based Kalman filter. It allows to cancel the drift of the inertial navigation model. And so with this system, we are able to find the orientation of a board in real time, and everything is computed on one single GRISP board. So this example really pushes the GRISP-Base board, the driver, and the Erlang numeric computation to their limits. Oh, and there is a video link if you want to see the system in action. Our conclusion is that Hera gives satisfactory results for simple sensor fusion. Because we make no use of cloud, it is simpler, cheaper, and more reliable. Hera offers a high-level approach with a focus on sensor fusion. There is no soldering, no need to read through datasheets, and there is no development with a low-level language. Hera is fault-tolerant, easy to use, low-cost, and open source, which makes it an ideal candidate for education and prototyping. We think that Hera is the best existing Kalman filter-based sensor fusion framework for low-cost prototyping. Future work with Hera involve performance improvements. There is the GRISP-2 board that should be 10 to 20 times faster. We also expect improved drivers, and we are working on a new matrix library that should be 10 to 100 times faster. And the good news is that all of these should be available by the end of 2021. Possible experimentations with Hera involve machine learning, for example, motion recognition. We think that machine learning and Kalman filter have a different purpose, but they are complementary. One could be the input of the other, or the other way around. And we would also like to attempt controlling a physical device or targeting rugged terrains because Hera is fault tolerant. So given the success we had with Erlang in our research, we really encourage more work in IoT with Erlang. Thank you very much.